All right, welcome to part 2. So this distance formula that we just went over, so let's look at an example of how we can use this to find segment lengths. So in the picture here, so we have the coordinate plane and we have a whole bunch of different segments. And so we need to find the length of AB and CD and then determine if they're congruent or not. So see if they have equal lengths. So first we need to find AB. So using the distance formula, we are going to, let's say what A is and what B is. So A from the graph, let's go find the coordinates. This is at 0, 3. And then B, we look in the graph, is 5, 1. All right. And we are going to label them just like we did with the midpoint. So A, there's our x1, y1. So that's, again, just saying that, hey, this is my first ordered pair, so one of my endpoints. And then B, x2, y2, the 2's indicate that here's a second ordered pair. So using those x1, y1s, x2, y2s, we can plug into our distance formula. So the distance of AB equals, and then a big square root, and then just plug in and then take it one step at a time to simplify. So AB, so A or B is my x2, so I'm going to look for x2, which is 5, subtract my x1, which is 0, and then y2 is 1 minus y1 is 3. All right, so that's plugging everything in. And then when you're simplifying, just think about your order of operations. The square root is going to be the very last thing you do. So kind of first work inside and simplify all of this. So first do your parentheses. So 5 minus 0 is just 5. And then the second set of parentheses, 1 minus 3 is negative 2. Next are your exponents. So square the 5, you get 25. Square the negative 2, which is 4. And then add those together, you get 29. And then the last step would be to take the square root. Because the 29 doesn't have a square root, I'm not even going to bother figuring what that is in my calculator. I'm just going to leave it as square root of 29. Because then what I want to do is find CD and then see if they are the same. I'm running out of room here. So let me do CD over here off to the right. So CD, kind of same thing. I first want to identify what my C and my D points are. So C is at negative 1, 1. D is at negative 3, negative 4. So C, negative 1, 1. D, negative 3. That's not my eraser. Negative 3, negative 4. All right, so then plug that into the distance formula. So let me label first. Getting ahead of myself. So C I can label as x1, y1, D, x2, y2. So now plug it in. So in my distance formula, so x2, get this out of the way. Oh, there we go. Negative 3 minus x1, which is negative 1 squared, then plus y2, which is negative 4, minus y1, which is 1 squared. All right, so then now simplify inside the parentheses first. So negative 3 minus a negative 1, it's really plus 1, so that's negative 2 squared, plus, and then negative 4 minus 1 is negative 5 squared. Then do your exponents. Negative 2 squared is 4. Negative 5 squared is 25. And then look, add the insides together there. You get square root of 29. And then so square root of 29 equals square root of 29. So therefore AB is congruent to CD. They have the same length. Okay? So that's the distance formula. All right, now we're going to finish up with looking at a right triangle, which we are going to study a lot more in depth later this year, but just kind of give you a little piece here about the relationship between the three sides of a right triangle. So first we need to know a few terms in order to understand this. So in a right triangle, we have what are called the legs and the hypotenuse. So the legs are the two sides that are adjacent to the right angle. So if you remember, adjacent means like next to, okay? So here's one leg, here's one leg. So the two sides next to the right angle. Or you can think of it as the two sides that actually form the right angle. And if you look to see where those two legs meet, that point, that's the right angle right there, okay? They form the L. And then the longest side across from the right angle is called the hypotenuse. So then the Pythagorean theorem is this relationship between those three sides. And what it says is that the sum of the square of the lengths of the legs is equal to the square of the length of the hypotenuse. So the sum of the square of the legs, and I'm going to write this two different ways, right? So if you square the leg, sum means you add together, so square the length of the other leg. That is equal to the square of the hypotenuse. So whatever the hypotenuse length is, raise it to the second power. But another way you might have actually already heard it already is a squared plus b squared equals c squared. And looking over at the picture to the right, you can see that the A and the B are those lengths of the two legs, and C is the hypotenuse. So A squared, so whatever that length is, square it, plus B squared equals C squared. So let's kind of look to see how we can use that and how we can relate it to the distance formula. So here we have a right triangle. You have the ordered pairs given for A and B. And we want to know what's the distance from A to B. So first we're going to use the distance formula, but then we also are going to show it using the Pythagorean theorem. So let's first just try the distance formula. So we have that our A is negative 2, 3. So that's going to be our x1, y1. And then our B is 2, negative 2. So that's our x2, y2. All right, so then in our distance formula, from A to B, the distance is as follows. So our x2, which is 2, minus our x1, so that's negative 2, plus, and then y2, so back down to the order pair B, grab the y coordinate, minus y1 from A. There we go. So simplify. So 2, this is really plus 2, so 4 squared. And then negative 2 minus 3 is negative 5. Okay, so remember you do inside the parentheses first, then do your exponents. Oops. All right, then add inside the square root. So 16 plus 25 is 41. And then I'm just going to leave it like that, okay? So square root of 41. There is no square root of 41. You can't simplify it down anymore, so we'll leave it like that. All right, now let's see if we can get that using the Pythagorean theorem. So now we don't need to worry about these ordered pairs anymore, but instead we want to look at side lengths. So if I look at this bottom side from C to B, so that length of A, and figure out, well, what's the distance? Well, all I have to do is really count, right? So 1, 2, 3, 4 units. So A is 4. And then B is the other leg over on this side. And because it's a vertical line segment, all I have to do again is just count the units. So that's 1, 2, 3, 4, 5. So B equals 5. And then C is our unknown. Okay, C is our hypotenuse, which also happens to be the length of AB. Okay, so using the Pythagorean theorem, if we solve for C, that's going to be our length AB. So again, the Pythagorean theorem states that A squared plus B squared equals C squared. So I'm going to just substitute in 4 for A, 5 for B, and then I'm going to solve for C. So our order of operations are to first do the exponents, so 4 squared and 5 squared. And then add 16 plus 25, which is 41. And you're always going to come down to something like this, where you have a number equals and then either A, B, or C squared. So then you have to ask yourself, how do you undo a square? And that's the square root. So square root of 41 equals C. So both came out to be the same. So we know we did it right. And so we verify that the length of A to B is 41. Now it does say to round to the nearest tenth. So let me punch that into my calculator real quick. So square root of 41. So we could say AB is approximately 6.4 units long. All right, here's our final application of using either distance or Pythagorean theorem. So here we have a baseball field, we have the 4 bases, and it's like overlaid here on top of a coordinate plate, so we can see the ordered pairs. And the question is, if the player throws the ball from home plate all the way to second, what is, oops, my highlighter is not really working too well. What is the length of that throw? Oops, it's highlighting everything now. Okay. So let's kind of look and see what we have here. So we have, again, let me try to highlight, here we go. So the length from home plate to second, or from H to S. And notice we can make a right triangle out of, oh my gosh, this is not good here. All right, try that again. So we can make a right triangle going from home plate to first to second. There we go. And because these units are horizontal vertical, we can just count the units, but notice it's not going by ones. So if H is starting at 0, looking at our x coordinate over here at first base is 90, that's just 90 units long. And then because it's a square, and it's the same distance from first to second, that is also 90. So if we think about this right triangle in terms of A, B, and C, those are both our legs, A and B. Okay, those are the two sides that form that right angle right here at first base. And then the hypotenuse, which is the length we're trying to find, is C. So A squared plus B squared equals C squared. Plug in 90 for A and B. And solve for C. So first thing I'm going to do is do my exponents. So 90 squared is 8100 plus another 8100 equals C squared. And then add 8100 plus 8100, 16,200. And then take the square root of both sides. And you get that C is approximately 127.3. And there you go. And that's in feet.